Dear students, we are on the CEC Gurukul lecture and we are in the series of electronic circuits. We are discussing the various electronic components which are used in the electronic circuit. In today's lecture, we are discussing the rectifier. What is a rectifier? Which converts AC into the DC current, alternating current into the direct current. And rectifiers are of many types, which works in the single phase as well as the three phase. So we discuss the up to now we discuss the half wave rectifier and the full wave rectifier. We are discussing the bridge rectifier. Bridge rectifier which uses the four diodes which are connected in a unique arrangement. Now you see on the screen that this is the bridge rectifier which convert the alternate current into the direct current, and it uses the full cycle, that is the full bridge rectifier. It converts positive and negative cycle of the alternate current into the output. As you see on the screen on the right hand side, you are seeing the alternating current positive and alternating current negative cycles. The full output we will get in this type of rectifier, and here we are using the we are using the four diodes, D1, D2, D3 and D4. As we know that these four diodes are used where in the one half cycle D1 and D2 conduct and the another half cycle D3 and D4 conduct. Means once D1 and D2 will work in the D1 work in the forward bias, and in the another part D3 work in the forward bias. During the first half, current flows from A through the D1 through the load resistance and D2 back to the secondary. You see here going towards the load resistance, and again through the D2 it will be going back. Similarly here in the another D3 and D4 arrangement, the current flows through the D3 and through the D4, it will back to the secondary. In both the cases, current flows through the load resistance in the same direction, producing the positive signal, as we have shown in the output. Thus the bridge rectifier also gives a full wave output. Now this is the bridge rectifier which is using the D3 and D4. The D3 is in the forward bias and D4 will give the output. Now the working of the bridge rectifier, if we discuss, then it contains a unique arrangement which gives it the converter. The diodes are connected in a particular fashion, as you have seen that D1, D2, D4 are arranged in a like a bridge. In the bridge rectifier, the voltage that is given as the input can be from any source. So this transformer is used to step up and step down the voltage, or it can be from the mains of our domestic power supply. So the first phase of the working of the rectifier, during the positive half cycle, diodes get forward biased and conduct. Diode D1, D4 get the reverse bias. We can keep any diode as a reverse, any diode can a forward bias. Just we want to get the one diode as a forward bias and another diode as a reverse biased, and then we can get the output for both the cycle. Thus we get the positive half cycle, the output conversely. In the negative half, diode D1, D4 get the forward bias and they start conducting, whereas the diode D3, D2 gets the reverse biased and do not conduct. The biasing can be done accordingly. Means when we get the output, we have to make the any diode as a forward bias. Again we get a positive half cycle at the output. At the end of the rectification process, negative half of the AC current is converted into the positive cycle. Means in the DC we are having all the positive output, like as we are having the positive and we are having the negative cycle in the alternating current, but in the direct current we are having all the positive output. So the output from the rectifier is two half positive pulses with the same frequency and the magnitude as that of the input. So we get the output of the alternating current. What are the advantages of the bridge rectifier? The low ripples in the output DC signal, the high rectifier efficiency we will get in this bridge rectifier, then low power losses we are having in the bridge rectifier. What are the disadvantages of the rectifier? Bridge rectifier is more complex than the half rectifier because a number of diodes are we using more here, more power loss compared to the central tapped full wave rectifier. So next topic is the center tap rectifier, which is used for the output. The type of full wave rectifier uses a central tap transformer. Here you see on the screen, and it is using the two diode transformer and the two diode. Means we are having a one center tap transformer and the two diodes. A center tap transformer is a dual voltage. Here you see that has the two input I1 and I2, and the three output terminals T1, T2 and T3. So central tap rectifier is containing the two diode and one tap transformer. The central tap transformer is the dual voltage transformer that has the two inputs T1, I1 and I2, and output, and the three output terminals T1, T2 and 3. On the screen you are seeing that I1, I2, and right hand side that there will be the T1, T2 and T3 as an output. Now the central tap, the T2 terminal is connected to the center of the output coil. This is the center which acts as the reference ground to the voltage reference. So the terminal T1 produces the positive voltage and the T3 terminal produces the negative voltage with respect to the T2. Here see that again we will have that the T2 terminals connected to the center output coil, that will be the reference ground to the voltage reference. What is the T1? T1 produces the positive voltage, and what is the T3? T3 terminal produces the negative voltage with respect to the T2, which is the output coil. Now controlled rectifier, this is type of the center tap rectifier. According to that we can get the output. Now the another type of the rectifiers are the controlled rectifier. This type of rectifier where we can control the voltage, or the voltage can be vary, as known as the controlled rectifier. So what we use in this control rectifier? We use the SCR, MOSFET, IGBTs to make a controlled rectifier, a controlled one. To making the rectifier controlled, we use the SCR, MOSFET and IGBT. These rectifiers are preferred over their controlled counterparts. Now there are two types of controlled rectifier. One is the half wave control rectifier, second is the full wave rectifier. Again, half wave control rectifier we can get the half output, and the full wave rectifier where we can get the both the cycle output. Now the half wave control rectifier has a same design as that the half wave of the uncontrolled rectifier, except we replace the diode with the SER. What this is SER? This SER is the silicon controlled rectifier, which is used to control the voltage. In the uncontrolled we are using the diode, but with the diode here we are using the silicon controlled rectifier. Now you see on the screen that this is a half wave controlled rectifier. The half wave controlled rectifier is made of the single SCR silicon controlled rectifier. You see left hand side is the input and output is the in this manner. So half wave controlled rectifier, we can control the output of this rectifier, so diode with the SCR. Now half wave control rectifier, controlled rectifier has the same design as that of the half wave uncontrolled rectifier, except we replace the diode with the SCR, as we are having the SCR does not conduct in the reverse bias, so it will block the negative half cycle, so no need to back, so it will block the negative half cycle. On the positive half output we will get. During the positive half cycle, the SCR will conduct current on one condition, when a pulse is applied to the gate input. Now the gate input is the periodic pulse signal which is designed to activate the SCR at each positive half cycle. In this way we control the output voltage of the rectifier in the controlled manner. The output of the SCR is also the pulsated DC voltage current. These pulses are removed by using the capacitor parallel to the load resistance. Here you see, with the load resistance, a capacitor is also added. This capacitor is used to get the output, and when the output of the SCR is also pulsating the DC voltage, these pulses are removed by using the capacitor and parallel to the load. In the full wave rectifier, full wave controlled rectifier, a type of rectifier that converts both the positive and the negative half cycle of the AC and DC, as well as control the output amplitude, is known as the full wave rectifier. You see here in this type of rectifier, we can change the amplitude also, we can change the output, we can get the output in a controlled manner. A type of rectifier that converts both the positive and negative half cycle of the AC and DC and control the output in terms of its amplitude, and that is known as the full wave control rectifier. Just like the uncontrolled rectifier, similarly the full controlled rectifier has a two type. One is the controlled bridge and second is the central tap. In the controlled bridge rectifier, the diode, with the diodes we are using the SCR. Thyristors are used bridge with the same configuration as we are having. Now you see, with the 4 diodes are used with the load resistance and the battery. Second is a control tap rectifier. It is also that type of rectifier where just like the central tap control rectifier, this design uses the 2 SCR replacing the 2 diode. Both of these SCR switches too will be timed differently according to the input AC frequency. This operation of the same as that of the uncontrolled rectifier. This is again the controlled center tap rectifier with the capacitor. You see, with the load resistance, a capacitor is also attached here. The 2 terminal T1 and T2 where we can get the output. Now, what is the comparison between these 3 rectifiers? Now, we see that the half wave rectifier is the simplest and the cheapest form. Half wave rectifier, but the output of the one type we will get here, the other 2 we will not get, but the output contains only the one half. In the others we can get the full cycle. Now this makes the more difficult to convert the fluctuating DC to the pure DC. Means we are not getting the continuous DC, but a fluctuating DC we will get. The central tap transformer is the must be the full wave rectifier. Now the half wave and the bridge rectifier circuit can also be drawn without the power transformer, but in the center tap we use the transformer. In that case we may have to use the high resistance to reduce the voltage to the required value. Now in the full wave rectifier, voltage is taken across the one half of the secondary, hence the number of the turns in the secondary will be the double for the central tap full wave transformer compared to use of the bridge circuit. Voltage output turn is more for the bridge rectifier transformer. Now what are the applications of the rectifier? There are the many applications of the rectifier. It is used in the many circuits as it converts whenever we require the DC current, then we use the rectifier which convert the AC current into the direct current when we require. So rectifier are used in the electrical welding and it provides the polarized voltage. Half wave rectifier used as a mosquito repellents. Half wave rectifier are used as a signal peak detector in the amplitude modulation radio, AM radio, and that will be the controlled output. Rectifier are used in modulation, demodulation and the voltage multipliers. This is a comparison chart of half wave, full wave and this is a full wave center tap rectifier and the full wave bridge rectifier. So these are, here we are having the basic properties in this type of three types of rectifier. Number one is the number of diode. In the half wave we are having the single diode, but in the full wave center tap we are using the 2, but here in the bridge we are using the 4. Similarly here there are the other parameters, DC current, transformer necessary, and transformer necessary you see only in the full wave center tap rectifier. Other tools not necessary will be use the transformer. So maximum value of the current is also given here and on the screen. Ripple factor is also mentioned here, and almost the center tap and the full bridge rectifier having the same, and output frequency is mentioned here. Maximum efficiency, the maximum efficiency more in case of the full wave tap rectifier and the full wave bridge rectifier as compared to the half wave rectifier. Peak values will be more, peak inverse voltage will be more in both the full wave rectifier. So these are the comparison chart. Now we are using the bridge rectifier. So one of the application and one of the best example of the bridge rectifier is the Wheatstone bridge, where we use the 4 diodes and which we can find out the resistance. So Wheatstone bridge is also known as the resistance bridge, which calculate the unknown resistance by balancing the two legs of the bridge circuit. Two leg means we are having the D1, D2, D3, D4. So Wheatstone bridge is the one type of the resistance bridge which will give the value of the unknown resistance. One leg include the component of the unknown resistance and another one is having the different resistance. So in the Wheatstone, how the Wheatstone bridge constructed, the Wheatstone bridge circuit consists of 4 arms, means 2 arms consist of the form known as the resistance, while the other 2 arms consist of the unknown resistance. Because we are calculating the unknown resistance, 2 known resistance are having there, and the variable resistance, 2 unknown resistance are the variable resistance. The circuit also consists of the galvanometer and the electromotive force sources. So the EMF source is attached between the points A and B, while the galvanometer is connected between the point C and D. We will see in the diagram. The current that flows through the galvanometer depends on the potential difference. So the again we see that that first Wheatstone bridge works on the principle of null deflection, and both the bridge should be balanced. Both the part which both the legs must be balanced. 2 attached with the 4. In the 4 we are taking the pair, 2 pair, so both the pair must be balanced. So that is the ratio of the resistance is the ratio of the resistance is equal to no current flows through the circuit. Then we will get the null output. Deflection will be in the form of the null. So under the normal condition, the bridge is an unbalanced condition where the current flows through the galvanometer, and it will show the deflection of the 0. The bridge is said to be balanced when no current flows through the galvanometer. This condition can be achieved by adjusting the known resistance and the variable resistance. So at that point the known resistance will be adjusted accordingly by putting the value in the unknown resistance, so that we can get the balance output, or we can get the output in the galvanometer as in the form of the 0 deflection. So this is the, you see on the screen, then this is the Wheatstone bridge. Here see P, Q, R, S are connected with the battery. This is a very simple arrangement, and you see P, Q, R, S, in between that we are having a G, that is a galvanometer. Then the deflection will be the null point when both the unknown resistance balance, then we will get the output. So this is the Wheatstone bridge. This is the circuit of the Wheatstone bridge, where we see the 4 resistance and the one galvanometer and one the battery. You see, current will be flow in this manner. Now this is the condition when the two current flows through the galvanometer, and it can be achieved by regulating the variable resistance and the unknown resistance. For this we have the condition PS is equal to RS. Both the pairs must be balanced, where the R is the unknown resistance and P and Q are the ratio arm of the bridge, and S is the standard arm of the bridge. So which is equal to R is equal to P by Q into S. So then S is adjusted to the value where the null condition is met. So derivation of the Wheatstone bridge, in this we can see that the current arrives at the galvanometer and divides itself into the two equal currents like I1 and I2. So when the current through the galvanometer is 0, means I1 is equal to I2, then I1P is equal to I2R. Then balance in the balance condition, the current of the bridge is expressed as follows: I1 is equal to I2, so I1 is equal to I3 and I2 is equal to I4, E divided by P plus Q, E divided by R plus S. Hence the EMF of the battery is E. So I1 and I2, after replacing the equation, we can have RE divided by R plus S, PE divided by P plus Q, P R plus S, R PQS, and in this manner we can get the output as the R is equal to P by Q into S. So hence we can get the balance, we get the null condition of the bridge, and in that equation, and also the R is the unknown resistance and P and Q are the ratio arm of the bridge, S is the standard arm of the bridge, then S is adjusted to the value, the null condition we will met. So what are the application of the Wheatstone bridge? Wheatstone bridge is used for the precise measurement of the low resistance. We can find out the unknown resistance, unknown low resistance through this Wheatstone bridge. Wheatstone bridge and an operational amplifier are used to measure the physical parameters such as temperature and light and strain. And another application, quantities such as the impedance, inductance and capacitance can be measured by the variation of the Wheatstone bridge, and measurement of low resistance by means of the direct application of the Ohm's law cannot be done accurately. Therefore, in such cases, Wheatstone bridge circuits can install for accurate measurements. And what are the limitations? Low resistance measurement. So we cannot find out the high resistance, the resistance of the leads, leads and contact before significant and introduces the errors. High resistance measurement, the measurements presented by the beat is large, that the galvanometer is insensitive to imbalance, so we cannot use. Another drawback is the resistance changes due to the current heating effect through the resistance. Excessive current may even cause a permanent change in the value of the resistance. It is a very sensitive device, therefore it is possible that the measurement using the Wheatstone bridge may not be precise in the off balancing condition. There are many more drawbacks of the Wheatstone bridge, and there are many applications of the Wheatstone bridge. In the electronic circuits we use the rectifier. Thank you very much.